As another example, here are actually four more compounds. Again, showing the vapor pressure of each as a function of temperature. So this is diethyl ether, ethyl alcohol, water, and ethylene glycol. So you can play the same game and try to figure out which one of these, what the relative strength of the intermolecular forces are. And since it's up here, why don't we do that? So there's always a few ways you could do it. You could compare the vapor pressure that these compounds exert at a particular temperature, but in this case you actually have a hard time finding temperature. Actually, you do. So if you look here at about 20 degrees, you can see that the vapor pressure of water is barely registering here. The vapor pressure of ethyl alcohol or ethanol is a little bit higher, and then for diethyl ether it's way up here. So remember, those two are inversely related. The greater the pressure, the weaker the intermolecular forces. So what that tells us is the diethyl ether has the weaker intermolecular forces of this bunch. The ethanol comes in, is next. The water is the strongest of those three. And since the ethylene glycol isn't even registering on the scale at that temperature, you can safely assume that that's the strongest of the bunch. All right. But let's get mathy. So the relationship between the temperature and pressure is clearly not a linear one, because these aren't straight lines, they're kind of curvy. And there is an actual equation that describes them that's beyond the scope of this particular class, but not beyond the scope of physical chemistry, which you can take your junior and senior year if you decide to become a chem major. So I'll just give you the answer. So let's look at any one particular curve, and it's actually exponential. And the relationship is that the pressure is proportional to E to the 1 over temperature. So the vapor pressure increases exponentially with negative inverse temperature. This, by the way, is an equation that comes up a lot in nature. And if you want to make it an equality, the pressure is equal to some constant times E to the negative B over T, where again T here is the absolute temperature. And the question here is, well, what are these constants A and B? Turns out the constant A doesn't have much of a physical meaning that matters much, but the constant B does, and that is equal to the enthalpy of vaporization divided by this constant R. And this R is the ideal gas constant that we use in the ideal gas law, but it's just expressed in the joules per mole per Kelvin units. And again, this here is the enthalpy of vaporization, so this is the measure of how strong the intermolecular forces are, how much energy you have to put in to break them. So looking at that equation again, and very often you will find it expressed like this. So the way that you undo this exponentiate, or this E or exponentiation operation, is you take the natural log of it. So to get rid of this E expression, you take the natural log of both sides. So the natural log of the vapor pressure is equal to the natural log of this constant A, and then minus delta, the enthalpy of vaporization, divided by RT. And the reason why people do this is way back when you didn't have computers, on your wrist or your hip pocket, that linear equations were by far easier to analyze than any other type of equation, because they don't require a computer, they require a ruler or anything with a straight edge on it. And this, in fact, is a linear equation. So if you map it against the generic y equals b plus mx, and here b is your generic intercept b, it's not the b from the previous equation. But so the y, so you're gonna, the y-axis is the natural log of the pressure. The intercept is going to be the natural log of this A constant. And here's the one where you have to think about it a little bit. So this is the slope times the x variable. And in this case, the x variable is 1 over the temperature. And the slope is going to be delta H over R. So let me show you what that looks like when you plot that. So again, to get this linear plot, you do the natural log of the pressure on the y-axis and 1 over the absolute temperature on the x-axis. Remember, it's always y versus x. And if you do it that way, you get something like this. And the nice thing about this is, so if you measure the vapor pressure at a bunch of temperatures and you make it plot like this, you can determine the enthalpy of vaporization of a particular compound. So the slope of this line is equal to negative delta H of vaporization over R. So if you multiply your calculated slope by negative 1 over R, then there's your enthalpy of vaporization, and that's how these things are measured.